Hello and welcome everybody to the screencast on the Argo Problem is Existential or Complete. Here I present some joint work with Mikkel Abbrahamsen and Anna Adamaszek. This is Mikkel, this is Anna, and this is me, Tilman Milso, or just Til. So in this talk or in this screencast, I will first define you what is the art gallery problem, what is existential R. Then I will present you the main theorem. I will give you a short intro into this complexity class existential R and some closely related work for the art color problem. And then later I will be able to give you more theorems which kind of follow from what we did and some further consequences. Okay, let me start with the definition of the art color problem. So it was originally introduced by Viktor Klee in 1973, and he asked how many cards I needed to cover a polygon with n vertices. So there's a polygon with n vertices. And let's say I place a guard here, then the guard is covering everything that is seen. And what is seen is wherever there is no obstruction. So the line segment between the point here and the guard should be fully contained in order to be seen. And then these 6 points here, they cover the whole polygon, but actually those 4 points would be sufficient. And we're looking for really smallest sets of so-called guards covering the whole polygon. And here it's easy to see that this really is the smallest set because there is no guard who can possibly see 2 of these crosses simultaneously. We have 4 of those crosses, meaning we need 4 guards and we have 4 guards. So that is the definition of the Argo problem. Given some polygons, we want to find small sets of guards covering everything. And there is an important distinction here. All the guards that I drew were on the vertices of the polygon, but actually in the remainder of the talk, the guards could be anywhere inside the polygon. This is sometimes referred to as a point guard problem or interior guard problem. I will not mention this, they don't emphasize this, and this is really the classic variant originally from Victor Klee. Okay, so now you know what is the art gallery problem, what is existential R, which is somehow more difficult to explain because it's not a geometric problem. The existential R is a complexity class, and it's just anything that reduces in polynomial time to the computational problem ETR. So that's a computational problem. That's a complexity class containing many computational problems. Okay, ETR stands for existential theory of the reals, and it asks if such a formula is true, like you ask if there are real variables such that they satisfy some phi. So what could be phi? Phi is a formula, a logical formula using variables, constants 0 and 1, equalities, arithmetic operations, Boolean operations, this is and, this or, this not. Okay, so all kind of formulas that you could create in this way, but they must be well-formed, and well-formed meaning, they must be sensible. So let's see an example of what means sensible. So here, for instance, I ask for 3 real variables such that this equation is true and that inequality is not true. So I should not have in this part like an and or, but this should be only one equation. And the brackets should be in useful sense, in useful manner be placed. Okay, and so that would be an example of a formula I could represent. Here 12 is shorthand notation for 1 plus 1 plus 1, and so on and so forth. And this is sometimes referred to as a real analog to MP, maybe. So why? Because here you ask for real variables. In NP you ask for Boolean variables, satisfying a formula with in NP only Boolean operators, and here you have also the arithmetic operators. So that's why it's a real analog to NP, and it's somehow a stronger class. Okay, so what is now the main result that we have? The Argo problem for simple polygons, meaning polygons without holes or self-intersections, with integer coordinates is existential R. So you've given a polygon with integer coordinate, you ask what is the minimum number of guards, and then to decide this is existential R complete. That's the main theorem. Pretty simple. I really like the the result for two reasons. It makes this class, kind of small class existential R, larger by adding there an important, well-studied problem, putting it inside. On the other hand, the Argo problem has been studied now by 44 years, and the complexity has not been decided. We don't know the complexity, and now we captured the complexity by making it equivalent to many other problems, which I will introduce to you. Okay, so let me give you this introduction to existential R. So why it's important? Is it a complexity class by its own? So what we know so far is NP is contained in existential R. This is just because existential R is by definition more powerful. In NP we reduce we could define as everything that reduces to satisfiability, where we just allow Boolean operators, and here we allow Boolean and arithmetic operators. So this is trivial. But very difficult is that actually existential R is subset of p-space, which kind of is a long series of research led to that. But for both containments, we don't know if it's proper. Knowing if we would know it is proper, that would be a tremendous breakthrough in computational, in theoretical computer science, because it would imply that we could distinguish NP from p-space. If one of them would be equal, that would be also great, because we did a lot of research on existential R already, and then we would know more precisely where it lies. But yeah, somehow we wouldn't expect this because there's already this research going on, so at least not very soon we can expect it. But also let me give you a toy example for an existential or complete problem. So somehow this class appears often in computational geometry. Here, recognition of segment intersection graph. So what is this? You have as input a graph, and you ask, can you represent it as a segment intersection graph? So what is a segment intersection graph of those segments? Well, for every segment you make a vertex, and you want that every or you define that any two segments that intersect have an edge between. So orange and light green intersect, so there's an edge between. Light green and brown don't intersect, so there's no edge between. So you ask if this graph can be represented, and then if the answer is yes, you because there is a representation. So you could ask, is this problem contained in NP? And natural candidate, so you can already see here that all the vertices you can assume rational coordinates, because you could just slightly make them longer and perturb them a little bit. And then a natural candidate, if you want to show NP membership, would be just the coordinates of all the endpoints of the segment, and then you can easily check if all the intersections appear. But this is doomed to fail. So we know that if we use an integer representation, there are some graphs which require, or a series of graphs which require exponential number of bits. That means that the coordinates are double exponentially large in the size of the graph. Yeah, so we cannot hope for this canonical, simple witness that we would first think of. And because this problem is ETR complete, hoping for a different witness would, like if you would show that a different witness would work, you would show existential R equals NP, and that would be a big breakthrough, because a lot of problems suddenly could be solved faster. Okay, so yeah, so one reason why I like this class existential R is because for that problem you would at first think that it's in NP because there's kind of a canonical candidate for witness, but then it turns out this witness doesn't work and you don't know what to do, and then suddenly all of those phenomena you can capture in one class. Suddenly we have a thing to say, oh, maybe this problem is harder than the other problems. Yeah, so that's a nice thing. Now let me tell you about a few other problems, so unit disk intersection graph recognition, minimizing crossing number of a given graph. Important problem is feasibility. This is kind of a special case, so you have a polynomial with just one polynomial and you want to know if it's zero or not. That is as hard as existential are. A very important problem in geometry is stretchability. Many problems reduce from stretchability, also segment intersection. Here you've given a set of lines, let's say, or curves, and you want to know whether there is a set of straight lines inducing the same phase structure as this. That is called stretchability. Visibility graphs and some problems in higher dimension realizing polytopes. I don't want to explain them so much, but yeah. So you see there's already a bunch of problems, but not a huge set. And we will see in the next years whether this will become a big class like NP or will be rather a side phenomenon. Okay, so to the Argo problem, I want to tell you about related work. So there are plenty of NP hardness results or other kinds of conditional lower bounds. Edouard Bonnet and I show W1 hardness, the approximation results for different variants of the polygon, the results for different variants of the Argo problem, different variants of how the polygon could look like, where the guards can be placed. Yeah, I found at least 10. Probably you could find much more. But usually for the variant, like for the main variant, there are no positive results except this exact algorithm by Michael Sharir, which is kind of an observation. If you know these hammers from algebraic, these algorithms in real algebra, they kind of have this hammer and then you suddenly have it. But that's the only known algorithm, and without it we don't know. If you don't use those tools, we don't know how to decide it. Okay, with Edouard Bonnet we could show that there at least exists an approximation algorithm, which was very nice. So now we can at least approximate the polynomial time the problem. Okay, then with Anna and Mikkel, we could find polygons which require irrational guards, showing that the canonical witness, maybe just giving rational coordinates, does not work. There's a bunch of practical algorithms, people who try to actually solve it, implement algorithm, and see how good they work in practical and simulated instances. But overall, really surprising is that the set of results is really small, despite the fact there's a huge amount of research on the Argo problem. So that I find most interesting. And our result can be seen as maybe an explanation for it. It's obviously not a proof, but they cannot prove that there are no results, but maybe that explains part of the difficulty. Okay, so let me now tell you about some more results that actually follow from our reduction. They belong to the story. So I want to tell them here as well. So okay, so remember in each area we have the EDR formulas, and then in our reduction we should get a polygon. But we also get we can also generate some rational numbers, such that they translate the solution of the guard set to a solution of phi. So it holds it for any optimal guard set. We can find some of those guards. Okay, so these are some of the guards. We will place them on the x-axis here, so the y-axis is 0, such that they give a solution to phi. So if you have any optimal solution of the guard set, take some of them, take the x-coordinate, and then translate them. This is just an affine transformation here. And they will give you a solution to the original formula of phi. So let me illustrate this. So this is our polygon with the optimal guard set here of 6 guards, right? Okay, that's just a toy example. So you take 3 of those on the x-axis, and they will give you a solution on phi. So this is not a one-to-one correspondence. We can move from here to there, but we can't move back, and there is a simple reason for that. because the solutions that might be unbounded, that our polygon is bounded. So if they're going too far, the solution would be outside the polygon. Obviously, that cannot work. So we have only a one-way correspondence. Yeah, so this is nice. So this tells you somehow that these solution spaces correspond in a nice sense. Yeah. So, and as a corollary from that, so we can even do the following. We can any algebraic number we can represent as a guard for in a polygon. So give me any algebraic number, then we can compute a polygon with rational coordinates such that any optimal guard placement, one of the guards has its x-coordinate alpha. So meaning in the optimal solution we can enforce any algebraic number to come up. Yes, this is very nice. So this shows a very strong link apart from this abstract hardness between algebra, real algebra, and the Argo problem. Okay, and this last corollary has an interesting consequence to potential geometric approaches that are doomed to fail. And I wanted to tell you about these potential geometric approaches, and you will immediately see why they fail. So what people do, I told you there is this practical algorithm, and what they do is they try to find a candidate guard set. So they say, we don't want to consider all these infinite guards, right? There are infinitely many potential guards. We just restrict ourselves to some guard set. And they may take the vertices of the polygon, for instance. And then they solve the Argo problem using only those guards. Then you can use brute force or integer programming as you like, and then you try to find a solution. And if that solution is not optimal, you have criteria for that. If that solution is optimal, then you can repeat. So you enhance your candidate set by looking at all kind of geometric things. So you say, for instance, at certain cells, I throw in another guard, or you look at intersections of a certain extension and you say, maybe I put one there, or intersection of extensions with edges of the polygon. And you can repeat this on and on and on. But if you do this, you're gonna stay with your coordinates inside Q. Meaning that you cannot find an optimal solution with this approach. This we already showed because with Mikkel and Anna we could show there are rational guards. But now I want to tell you something even stronger. So this failed. So now what's stronger is so that kind of naive approach to produce a candidate guard set, right? That failed. So let's do something more clever. So we look maybe at some, I don't know, you can do it in any way you like. You can produce curves of some bounded degree, let's say 20, okay? And look at all of those curves, no matter how you define them, and look at all potential intersections. I mean, that could be a really sophisticated, clever algorithm that you came up with, how you define those curves. But as long as all of those curves have bounded degree, these potential guards have also bounded degree. But we can get any algebraic numbers, and you will not get any algebraic number as long as you have only bounded degree polynomial curves that intersect. So also this fails. So really a large set of geometric approaches that you could go to find these candidate guards, you will not find the right one if you look at curves only of bounded degree. So there's like really almost no idea what could work. Yeah, so this is the consequence from dilemma. And so that all these approaches fail, this follows already from dilemma without having existential argument. Okay, at last I want to show you a technical result, which might be very useful for your existential R reduction. So let me just tell you, if you have an existential R reduction, you might either reduce from an already known problem of geometric kind, or you might directly reduce from ETR. And then usually what you have to do, you have to somehow simulate addition and multiplication, where multiplication is really the heartbeat. And we can get rid of this because we can show that if you can simulate addition and inversion, then you're already good. So what is inversion? Inversion is just x times y equals 1 instead of x times y equals 0. So let us define this algorithmic problem, ETRINF. That's a problem that asks if there are real numbers satisfying constraints of the form addition, a multiplication, or setting just the variable to 1. So that's kind of silly constraint, but we still need it. And even more, because we need it for the Argo problem, we can restrict all the variables between a half to. And we show this problem as extension are completed, and so all your reductions now, you can start from that, and they should work in a simpler manner. Okay, that was it, and thank you for your attention. And yeah, if you want to see the proof, they will come in other YouTube videos.